Greetings. This lesson is on ALEKS Module 8, so graphing rational functions. So before I get into an example, I just want to talk about some key points. When graphing a rational function, you want to look for any possible asymptotes. So these are lines that your graph is going to get really close to, but never actually touch. So we want to look for vertical and horizontal asymptotes. And we also want to look for any intercepts, so x-intercepts or y-intercepts. So just a general rule of thumb. You're going to find, and I'm just going to put in a generic here, ax plus b over ax squared plus bx plus c. I should use different variables here, but it's just to kind of give you the general idea. The zeros of your numerator, so zeros of numerator, will give you your x-intercepts. The zeros of your denominator will give you your vertical asymptotes. Now remember, when you express vertical asymptotes, those are actually equations. So you should express those as x equals equations, because when you graph them, we use the dotted line to represent that it's an asymptote. But when you graph them, remember, everywhere on that line, x is equal to the same value. So that's why your vertical asymptotes are x equals lines, and your horizontal asymptotes are y equals lines. So if you had a horizontal asymptote, everywhere on that line, y is equal to the same value. So make sure you always express those in x equals and y equals form. And typically what you're going to use them for is to actually graph, but in case you were asked for vertical or horizontal, that's how they should be expressed. Okay, so, and horizontal asymptotes we'll talk about in just a minute. Those are a little bit trickier. So let's start by graphing this example. And you can always check these graphs with a graphing aid such as Desmos or a TI-84 or TI-Nspire, a little fancier calculators. Those are awesome. So let me get this out of our way. All right, so first thing, do we have a zero of the numerator? No, because it's just 4. So this is telling us we do not have any x-intercepts. So no x-intercepts. We do have a 0 of the denominator. So that 0 of the denominator, if I set this equal to 0 and solve, gives me negative x equals negative 2, x equals 2. So we know that we have a vertical asymptote at x equals 2. So no x-intercepts and a vertical asymptote. So the only thing we have left to figure out is, do we have a horizontal asymptote? Well, there are very specific criteria for determining whether or not you have a horizontal asymptote and what it is. So I'm just going to go to this page for a second so we can... Oh, it's not here. That's okay. We're just going to talk about it. Oh, here it is. I was going to say I think my explanation's a little easier anyway, but okay, we'll go ahead and go through this. So if we have, let's just ax plus b, and let's just say this is cx squared plus d. So when you are looking for horizontal asymptotes, you are comparing the lead exponents. So in your numerator and your denominator. So see, I didn't have one written in, so it's assumed to be a 1. So these are the values that we are comparing. So in this particular example, N represents this top numerator, and M represents the denominator. So if your lead exponent in the numerator is less than your lead exponent in the denominator, then your horizontal asymptote is 0. Y equals 0. So if this value here is smaller than this value here, lead exponent, horizontal asymptote is y equals 0. If they are equivalent to one another, so let's say ax plus b over bx, not bx, sorry, cx plus d, then your horizontal asymptote is just the fraction of these lead coefficients. So then your horizontal asymptote would be y equals a over c, whatever those values are. So again, leading coefficient of numerator dividing by leading coefficient of denominator. That's if these exponents right here are the same. So they could both be x squared over x squared, or sorry, 2 and 2, 3 and 3. They just have to be the same. Then your horizontal asymptote is y equals the leading coefficients. And if your numerator is, the exponent in your numerator is bigger than the denominator, then you don't have a horizontal asymptote. So I highly recommend keeping this handy while you're going through these until you memorize it, because it is going to save you some time just to be able to pull out your notes and see, okay, I know how to find that horizontal asymptote. So let's go back over here. So we have our degrees here. This is to the power of 0, and this is to the power of 1. So in this case, this is smaller than our denominator. So remember, oops, I keep doing that and it just skips right over. So remember, if it is less than, then our horizontal asymptote is y equals 0. So then we know we have a horizontal asymptote at y equals 0. So now we want to do a rough sketch. On Desmos, or sorry, on Alex, you will have a grapher, so it's not quite as rough. So I'm just going to just want to get an idea of what this graph looks like. I like to draw in the asymptotes first. So this asymptote's easy. It's just the x-axis for your horizontal asymptote. Our vertical asymptote is x equals 2. So x equals 2, I'm just going to put in a dashed line. So I know, because I have an asymptote here and an asymptote here and no x-intercepts, I know that my graph is either going to go here and here, or here and here. But let's do some test points. There's no reason to guess. We could do something called the sign diagram, but I know Alex doesn't go through that approach just yet with its explanation, so I'll hold off on that. But a sign diagram would just kind of tell you whether or not your graph is above or below the x-axis. But plug-in points will do the same thing for us. So let's choose a value to the left of our vertical asymptote. So let's say, negative 1. So I'm going to plug in -1 to our equation here. Let's get that off. So I'm going to plug in -1, and that's going to give me 4 divided by -1 plus 2. So that's 4 divided by 1 plus 2, so 4/3. So I know that -1 4/3 is a point on the graph. So that's enough to tell me at least this part. So I know that I don't have x-intercepts here, and I know that this is a horizontal asymptote, and this is a vertical asymptote, lines that the graph will get close to but not actually touch. So that'll give me that lets me know that my graph is going to follow those asymptotes. So now I just need to see, where does the graph fall on this side of our vertical asymptote. So I'm going to pick a value greater than 3. So let's go with 4. So I'm just going to plug that in, negative 4 plus 2. So that's 4 over negative 2. So that gives me negative 2. So over 4 down 2, so I know that my graph is going to follow the asymptotes. So roughly, that's what my graph is going to look like. And you can always plug this into a grapher just to kind of see and double check your work. So I'm just going to pull this up real quick so we can, oh, oops, that's not the button I was looking for. There we go, Google. Let's go ahead and just pull in Desmos. So we are looking at the graph of 4 over negative x plus 2. Maybe I'm not going to plug in Desmos. Oh, here we go. So y equals 4 divided by negative x plus 2. And there we go. We should have, sorry about that, we should have also put in our y-intercept. But you can see here, you can see that asymptote happening at 3, and you can see our asymptote at y equals 0. And again, to determine your y-intercept, remember we plug in when our graph crosses the y-axis, our value of x is 0. So we would just plug in 0 for x and solve for y. So that's always a good point to plug into the graph as well. Okay. All right, so there's that first example. We've talked about horizontal asymptotes. So now let's try another one with a different scenario here. So we are going to graph this. I again like to start by dealing with the numerator. So the zeros of the numerator are going to give us our x-intercepts. So the 0 of 2x plus 3, so that just means I set it equal to 0 and solve. 2x equals negative 3, x equals negative 3 halves. So that is my x-intercept, negative 3 halves. So this graph does cross the x-axis. So now let's look at our vertical asymptote. So we have the 0. Remember, the 0 of the denominator is going to give you the vertical asymptote. So x plus 3 equals 0, x equals negative 3. So this we want to express as an equation because it is a line, x equals negative 3. So now let's look at our horizontal asymptotes. So horizontal, so we want to compare our lead exponents here. We've got a 1 and a 1. They are the same. So remember, if your lead exponents are the same, then your horizontal asymptote is expressed as a fraction, your leading coefficient numerator in the numerator divided by your leading coefficient in the denominator. So we are going to have a horizontal asymptote at y equals 2. So let's go ahead and find our y-intercept as well. So our y-intercept, we are going to plug in 0 for x. So that gives us a y-intercept of 0 plus 3, 0 plus 3. So 3 over 3, 1. So y-intercept is 1. Up here, that works. Okay, so now we have enough information to graph it. It says plot at least 2 points, so we'll pick one more point once we get a rough sketch going. All right. So we have 0 at negative 3 halves, so that's negative 1.5. So we have a 0 there, so we'll plot that point. We have a y-intercept at 1, so 0, 1 is our y-intercept. We have a horizontal asymptote at y equals 2. So I'm going to use a line there. It should be a dashed line, but this will just be a little neater. And then we have a vertical asymptote at x equals -3. That's a little far, so let's get a little closer. So at x equals -3. And I think my dash line might have actually been easier. So I'm gonna rethink that life choice and get rid of these. I don't like them. A little too much red going on there. All right. Good news is if I go too slow on things, you can just fast forward me when it's a video. Okay, so we have a horizontal asymptote at y equals 2 and a vertical at 1, 2, -3. So remember, our asymptotes are lines that our graph gets close to but never actually touches. So if I had to guess the behavior of this graph, I would say that it's going to go through my y-intercept, go through the x-intercept, get close to the asymptote. And then my other piece will be over here. So pick a value to the left of your vertical asymptote, so to the left of -3, and I would say that's just -4 is fine, and we're going to plug it in. So 2 times -4 plus 3 divided by -4 plus 3. So that gives us -8 plus 3 divided by -1. So -8 positive 3 is a -5 over a -1. That gives us 5. So we know an ordered pair on the graph is -4, 5. So I'm going to go over -4 and up 5. So again, I know that my graph is going to go through this point, and I know it's going to stay close to my horizontal and vertical asymptotes. And then I already have my y-intercept as a point over here. You could always plug in one more point if you would like, but that's what our graph looks like. This is actually called the graph of a hyperbola, which later when we get more into conic sections we will talk about. So never hurts to go to Desmos and plug it in just to see, the general shape in a more professional format. So plug that in. 2x, whoops, I need the 2x plus 3 divided by x plus 3. And there we go. Okay, so we can see our y-intercept at 1. We can see our x-intercept at -1.5. And you can tell that we have, let's get that out of the way, you can tell that this is approaching, let's move that, approaching -2, or sorry, approaching 2, approaching 2, so our horizontal asymptote. And then same here, you can see it's approaching -3 for our vertical asymptote. So we know that we did a pretty decent job on our rough sketch. Okay. So here, another example, a little different than the last one. We have a lead exponent that is bigger than, in our numerator, that is bigger than our lead exponent in the denominator. So we know right away, no horizontal asymptotes. None. Okay. We can still find our x-intercepts the same way that we normally do. We can still find our y-intercept. This function, though, has something called referred to as a slant asymptote. So slant asymptote. So let's start by finding the easy bits first, and then we'll come back to this slant asymptote here, which means it's not vertical and it's not horizontal. So zeros of the numerator, negative 2x squared plus 3x plus 3. Well, this is a quadratic, so we have a couple of choices. We could factor, or we could use the quadratic formula, or we could use a graphing calculator. Any of those are valid options. So let's go ahead and use quadratic formula. So a, b, c, so negative b plus or minus the square root of b squared minus 4 times a times c divided by 2 times a. So I always pay attention to signs first. I have a negative times a negative, so I know that this is going to be plus. I'm just going to get rid of that little negative symbol. So 4 times 2 is 8. 8 times 3 is 24. 24 plus 9 is 33. I did that very quickly. I just want to make sure. 8 times 3 is 24. 24 plus 10 would be 34, but it's 1 less, so it's 33. So negative 3 plus or minus the square root of 33 all over negative 4. Well, that's fun. Not exactly easy to graph. So at that point, I would go ahead and use a calculator and get those written in as decimals. Let's see. So I don't have my TI-84, so I'm just gonna cheat and throw this in here so we can see what that decimal value is. So parentheses negative 2x squared plus 3x plus 3. Look at that beautiful quadratic divided by 3x minus 9. Oh, you can see that slant asymptote going on there too. We'll talk about that in a second. Okay, so x-intercepts are right there. So negative 0.686. So negative 0.686. So that's what we would have gotten if we would have simplified our quadratic answer there. And 2.186. There we go. Okay, I just want you to, since we're doing a little preview here, I want you to be able to see there's two parts to this graph. So you can see that the asymptotes definitely don't have that normal horizontal vertical asymptote behavior. And this occurs when your lead exponent in your numerator is bigger than your lead exponent in the denominator. Okay, so now that we have our x-intercepts, let's go ahead and find our y-intercept. So I'm going to plug in 0 for x, so that goes to 0 plus 0. So that gives me 3. And this 0 minus 9. So we have a y-intercept of 1/3. So y-intercept is 1/3, which really we should express that as an ordered pair. So 0, 1/3. And here, ordered pairs for our x-intercepts. There we go. Okay, so the slant asymptote. How do I calculate that? Well, we calculate that by dividing our rational function. So we have negative 2x squared plus 3x plus 3. We're going to use long division and divide that by 3x minus 9 so we can have this equation in a different form. So 3 goes into negative 2, 3x goes into negative 2/3 x times. So remember, it's just like regular long division, so I'm going to multiply negative 2/3 x by 3x minus 9. That's going to give me negative 2x squared plus 6x. So I did 3 into 9, which is 3. 3 times 2, 6. And I had negative times a negative, so that's why we have positive. So then I'm going to write that here, negative 2x squared plus 6x. Notice how these are the same. If they aren't, you made a mistake. So with normal division, we would subtract. So it's minus these values. So I'm going to change both signs. That's all that subtraction does. So that goes to 0, which we expected to happen. This gives us negative 3x. Drop down our plus 3. 3x goes into negative 3x, negative 1 time. So negative 1 times 3x minus 9 is negative 3x plus 9. Again, we're subtracting. So change, just like normal division, so change both signs. So that gives me, that goes to 0. This goes to negative 6. So we have a remainder of negative 6. And remember, we write our remainders like that. All right. So how does this help us? We have this form here. Well, we want to look at what happens as x goes to infinity. So as x goes to infinity here, this is going to increase without bound. The reason we're looking at that is if you're thinking of asymptotes, we are looking at the end behavior of our graphs. Here, as x goes to infinity, what happens to this? 6 divided by a really big number. 6 divided by an even bigger number. Well, that's a fraction, so 6 divided by, say, 1,000,000 is going to be a really tiny number. So these are going to approach 0. So we're just kind of going to ignore this piece because we know that that's going to approach 0. So we're just looking at this piece here. Y equals negative 2/3 x minus 1. That equation is going to give you your slant asymptote. We also need our vertical asymptote. I just realized that we did not do that. So our slant asymptote is here. So we calculated that. So the steps for calculating that were dividing the rational function. Wow, I just struggled with spelling dividing. It's early. We're dividing the rational function. And then we're looking at that remainder, because that remainder is always going to approach 0. So then now we have an equation for our slant, because you can see that's a line. We'll just plot the line. So that's calculating the slant. So now we just need our vertical asymptote. So remember, zeros of the denominator give you your vertical asymptote. So we have a vertical at x equals 3. Okay. So if we were doing this by hand, we would first graph the line negative 2/3 x minus 1. And we would graph a line x equals 3. And we would plug in our x and y intercepts. So let's go look at our graph on Desmos. So let's keep that in mind. Negative 2/3. Oh, I was going to say somebody should have told me I forgot the x, but I guess you can't. So negative 2/3 x minus 1. Let's just graph that in here. Negative 2/3 x minus 1. Look at that. And let's graph x equals, I think it was 3, yes. Beautiful. Okay, so if we had been doing this by hand, and then we would have plotted this line and plotted our vertical asymptote, and then you can see this graph is getting very close to this line. It's getting very close to this line here. It's passing through our x-intercepts exactly the way we expected. Our y-intercept here at negative 1. Is that what I got? Why doesn't that sound right? Where's my y-intercept? Why do I have a y-intercept at 1/3? Let's see, so 0, 0, 3 over -9. That's -1/3. Where'd you go? Oh, there. Because I'm looking at the y-intercept of the line. Okay. So my point there, it is always a good idea to never just assume that a graph is correct. So look at it, think about things that you've calculated, and always, 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 always question. Okay, so that reviews slant asymptotes. Fun stuff, huh? Okay, let's get that out of my way. And that's just walking through it again. Again, walking through it. So if you wanted it written out nice and neatly, pause the video. And again, pause the video if you want it nice and pretty. You can see this is an Alex question. Okay. This is just wanted to do a quick review of finding x and y intercepts when problems aren't in standard form. So to find x-intercepts, we plug in 0 for y and solve, and to solve for y-intercepts, we plug in 0 for x. So let's find our y-intercept first. Wow, that was a struggle. Okay, so that gives us y minus 9 equals 0, y equals 9. So there's our x-intercept. So let's write it as an ordered pair, not as an equation. Sorry about that. So ordered pair 0, 9 is an ordered pair on the graph. That's our y-intercept. So x-intercept, x squared. I'm going to plug in 0 for y. Minus 9 equals 0. X squared equals 9. X is equal to plus or minus the square root of 9. So x is equal to plus or minus 3. So our x-intercepts are 3, 0, and -3.